So welcome back for the last talk of the meeting. Carlos will tell us about the potential of artificial intelligence illustrated in the classification of finite algebraic structures.
So thank you very much. So since this is the last talk of the week, I'd like to first take the opportunity to thank all the other speakers for a bunch of wonderful talks, and especially thank Pranav and Rukmini. Where's Rukmini? Thank Pranav and Rukmini for organizing this discussion meeting. It's been really fantastic. Okay. Okay, so what I'd like to talk about today, changing the subject a little bit. So I'd like to talk about finite categories and finite semigroups. Okay, so this is work that I'm doing with various people. It started really with my thesis student, Samer Alush. And then my current student, Najwa Ghanum, who Samer kind of sent me, you might say. And then David Alfaya, who many of you know from algebraic geometry, but he's also a brilliant computer programmer, and Edouard Balzin, a student from before, and also Boris Schwinke, someone who Edouard knows who works in Russia on computer programming. So we've been working on various different declinations of this project. So by way of motivation, let me just start with the finite categories motivation. But pretty quickly, we'll reduce to the case of finite categories with a single element, which is to say semigroups. But let me just briefly talk about Alush's thesis. So if you have so what's a finite category? It means the objects of A is finite. It's a finite set, and A of xi, xj is finite for all ij. And so then, once we choose an ordering on the set of objects, we can make a matrix. Mij is just the number of elements of Aij, A of x. We'll call this AI. And then the question is, what are the matrices? What are the possible matrices? And so I should also say that Tom Leinster wasn't really looking at this classification question, but he was looking at matrices of finite categories because he was using them for Euler characteristics. So let's say a matrix. And then Leinster had a paper with Clemens Berger from Nice. Alush gives necessary and sufficient conditions. So one kind of like a catchphrase, sort of a way of saying what the conditions are. I mean, this doesn't really say what they are, but you can say that that M is the matrix of A, if and only if all 4 by 4 are, all, let's see, R by R submatrices are so for R less than or equal to 4. In other words, the conditions only go up to things of size 4. 4, I think it's 4. In fact, so in the case we'll talk about, I'll just briefly mention today, that actually goes down to 2. So if let's assume that the entries are strictly positive, okay, that means that there's at least one morphism between any two pair of objects. And we're also going to say we're also only going to look for A reduced, which is to say no two distinct objects are isomorphic. And then in that case, the first statement, and this was just like a phrase in Leinster's paper, in fact, which is that if the diagonal entries are greater than or equal to 2, then A always exists. Okay? The construction is we define M prime ij equals Mij if I is different from j, and it's Mii, M prime ii is equal to Mii minus 1. Okay? The diagonal entries, and then we choose A prime, a semi-category, for M prime, which is to say no identities. Then formally add the identities. Then so 2 is that at most one diagonal entry with Mii equals 1. That's because of the reduced hypothesis. And then so 3, the main statement is that so we've reduced to the case where M has a single 1 on the diagonal. And now the condition is, so in this case, then Mij has to be bigger than or equal to Ai times Bj. Let's see, 1. I guess it's Bj, Bi times A. I guess. I mean, it's the product of the A and the B in the row and the column. And yeah, sorry, maybe I should have said, I mean, this means submatrices where you choose the same subset of rows and the same subset of columns. Are so. In other words, all submatrices correspond to categories. It just means that when you write down the conditions, it happens to only use up to 4 indices. And in fact, in this case, it only uses 2 indices, as you'll see. So this for the case where all the entries are strictly positive, then you could say R less than or equal to 2. As we'll see here, the conditions. I mean, the conditions just come from. No, sorry, this is even 3. Sorry. Yeah. Even here we have R less than or equal to 3. Yeah, sorry. This is because this plus 1 is because you have to have an identity object here, an identity morphism here along the diagonal, from xi to xi. This 1 comes from the identity for the object xi. I mean, so what it roughly speaking says, it says that if you take these maps from the first object to the other object and the maps in the opposite direction, their compositions to here have to be equal to 1. So there's left identities and right identities. And the compositions in the other direction all have to be distinct, basically. That's the content of the statement. So you can see this condition concerns only up to 3 by 3 submatrices, 2 by 2 for the diagonal ones, but you need 3 terms if you want it off diagonal. Right? The ij, that concerns I, j, and 1. Anyway, so I'm not going to say the case where it's more complicated but the same idea in the case where there's some zeros in the matrix. But so now this just contributes to sort of a philosophical question, which was my circus tent drawing there. Right? So here we have some inequalities. So you might say there's a question, which is, suppose we're near the inequalities. Then are the solutions somewhat constrained? I have to say we haven't actually worked on this. I mean, you'll see what we're doing now, but we haven't really worked on that question per se. Ganum is working on some version of this, a similar question. You might say, roughly speaking, when this 1 is replaced by having a group having a group of automorphisms of the object. You can make a similar type of a thing in the case where instead of having an object with a single identity, you have an object, but you assume that the automorphisms of that object form a group. So that's just kind of I say sort of philosophical motivation. And so now let me just point out that if you have a category with one object, then this is just what's known as a monoid. Sorry. Right, in other words, it has a so just an object, it's just something with an associative multiplication and an identity element, a unit element. And so as it turns out this unit element doesn't really seem to matter all that much somehow or other. As you can even see here, I mean, right, this construction, already in this construction, you see that like the real thing that's going on here is the semi category. So that's why but let me just say, so if we have a category, then the AII are monoids. So you can say a first question to studying the classification. So first question for the classification is to understand the classification of monoids. Then you might say a next question, this is a little bit what Najwa is working on her thesis. Like let me just say in parentheses, the next question is how can two different monoids fit together? In a two-object category. And so, well, actually, I mean, for the algebraic, we're in algebraic geometry here, right? So this type of idea, when you go back and look at Kapranov's, Bondal-Kapanov paper, for example, this idea of having a matrix is really very present, and even like in all of Kuznetsov type of things and stuff like that. The idea of like thinking of a category as like a matrix is very present, in fact. So here we're just like thinking of our category as a matrix, but then just taking the cardinality, right? But so you can really think of a category as being a matrix, right? We can think of a category as being a matrix where we put A11, A12, and so on. So I mean, these sets of morphisms fit into a matrix. Then there's some multiplication, and the multiplication even looks like matrix multiplication actually when you think about it a little bit. And so the question here is, can we put some monoid A11, A22? Then can we put something here and here to sort of link them together? But so, I mean, again, in order to start working on that question, you obviously need to know what are the possible choices here. So, you might say after starting off with categories and all that kind of thing. So in fact, you might say the logical first place to start or something. Is by looking at monoids. So let me just so before we stop, so then we'll stop talking about categories. But let me just say that in the question of just purely looking at monoids, you don't really see exactly, at least not really in any obvious way, this kind of phenomena. So I think the notion of finite categories as an extension of the theory of classification of semigroups or monoids, I think it still should be sort of interesting because you have this fact that you have some inequalities, and you can look at cases where it's close to the inequality. I mean, that just means suppose, like, for example, this was equal to this plus 1 or something like that, or plus 2. I mean, suppose this inequality holds, but the difference is small. And so the idea is that should lead to some kind of structure or something like that of the classification. And this is supposed to be analogous to what we were talking about in sheaves, vector bundles on, stable vector bundles on surfaces, for example. We have this, there's like a question of what type of maybe somewhat complicated combinatorial structure or classification structure are we going to have in sort of some intermediate range of some inequalities or something. But I don't know if you could possibly think of this as like a Bogomolov-Gieseker inequality or something. Not really, but that's that. The idea is to think of that type of thing. But anyways, okay, so now let's stop categories. Let's just talk about monoids. But so we can pretty much forget. So it's not really 100% true in the sense that if you have a monoid, you can just, that has a unit element, you can just forget that it's a unit element and call it a semigroup. If you have a semigroup that doesn't have a unit element, you can add a unit element to make it into a monoid by formally adding a unit element. But those two operations are not inverse, obviously. So there's not really a one-to-one classification between the two. But nonetheless, the one and one, I mean, when you start working with this, the one doesn't seem to be doing anything, just kind of hanging out and making things slightly more complicated even. So let's just, so a semigroup. A semigroup just means a set A with an associative multiplication. Now, on the other hand, what does seem to be a good idea, at least I can just, like, heuristically speaking, it does seem it does seem to be a good idea to suppose that there exists an element called 0 inside A, with the property that 0 times any object equals 0, and any element times 0 equals 0. Okay. This is some kind of very slight linear structure. So we'll see in a minute how that's important for the classification. I mean, we don't really have a classification, but important for trying to say something about the classification. And so let me just mention here that this fits in. I think we were discussing this just the other 3 days ago with Pranav, that we can really think of A with the 0. This is really an algebra. This is an F1 algebra. Depending on your definition of F1 stuff, but you know, F1 is the field le corps à un élément, the F1 fun, right? Depending on, there's lots of different viewpoints towards F1 stuff, but one of the viewpoints is that what corresponds to a vector space, the analog of a vector space is just a pointed set, and this is just, and the tensor product is just going to be a smash product of pointed sets, which is the product of the two pointed sets, but then you contract 0 times x and x times y, I don't know, y times 0, right? So we're going to we have a map A comma 0, sort of the smash product. How do you write this? And this is an associative. So this is really an algebra in that world of F1 stuff. But just so that's just sort of words or something maybe. But this 0 thing really does seem to work out to provide us a little bit of linear structure. So let me explain that. So, but now if you think about that this way, then you can pretty much import everything from like ring theory or something like that. In particular, there's a notion of left ideal, right ideal, and two-sided ideal. Right? You know, I inside A is the left ideal if A times I is contained in I. And two-sided if A times I. And so now, one kind of main construction that we can do, what construction can we make? We can make the following construction. Let's just call it an F1 algebra, right? In other words, a semigroup with 0. I don't know if there's, I mean, there's a Wikipedia page with like a ton of terminology for all sorts of different kinds of semigroups. I didn't notice a terminology for a semigroup with 0, which seems to be like the actual thing you really want to look at. So, but anyway, I'm going out on a limb there. I'm sure somebody will say, you know, Carlos, no, you're missing such and such. But anyway, so suppose we have one of these things, and suppose we have a two-sided ideal. Then we can define A mod I. So the point here is that the point is to really take this sort of philosophy fully, you might say, that the only linear structure is this 0 thing. So it means we don't want to make any kind of equivalence relation. We just want to contract I to 0. So this is just going to be A minus I disjoint union 0. Okay, we have a map from A to A mod I, where A goes to A if A is not in I, and X goes to 0 if X is in I. Right, so we just contract I to 0. And being a two-sided ideal is exactly the thing that you need to make this a semigroup and this a morphism of semigroups. Okay. Now we can say that, we'll say that A is simple. I guess in the book I saw by Jean-Eric Pain, this is called zero simple maybe. But since we're assuming there's a 0, I'll just not put the 0 there. So A is simple if the only two-sided ideals are 0 and A. Right, 0 and A are automatically two-sided ideals, and simple means those are the only ones. Another philosophical remark here is that this whole theory somehow there seems a lot like the theory of vector bundles, and I think if you know something about the theory of vector bundles, it's like sort of guides you a little bit into what to do here, as you'll see in a minute. But so let me just mention that. So there's actually a classification of these. So called the Rees. I assume it's the same Rees. I'm not sure if I'm getting that spelling right, but Rees-Sushkenich says that that a simple, like any simple F1 algebra is of the following form: A equals I cross G cross J union 0. Where G is a group, so I and J are sets. G is a group, and we have a matrix, we have a collection of elements P. PJI. We have a collection of elements of G or 0. Such that in any row or column, at least one is non-zero. And the multiplication is the following: that I comma G comma J times I prime G prime J prime. I should say it. So I got this this notation from a book by Jean-Eric Pain, but he says it's like well known and so on. So this is just so the idea here is I'll do this example in a minute, but the idea here is that the i's and the j's, they're just like dummy indices, so to speak. They just sort of stay to the outside where they are. So this is I. This is going to be J prime, right? The rightmost thing here stays the right one. The left thing here stays the left thing. In the middle, so we need to multiply G times J times I prime times G prime. So we're just going to take G times this PJI times G prime. That's if I prime is different from 0, or 0 if PJI prime equals 0. Okay. So this sometimes these can be 0, and that means sometimes the product can be equal to 0. Okay. That's just kind of easy to see that it's associative and everything. So these things are called Rees matrix semigroups. With 0. I don't know, I think there's like affinities between people. So I guess, obviously with Rees, there's some affinity with me, or something like that. Because the Rees construction was something I used a long time ago. Is it the same Rees? I don't know. I don't know if it's the same Rees or not. I mean, maybe that's over dramatization of the affair. But yeah, I'm not sure. I should check that. I'm sorry. Anyway, or maybe it's somebody of the family or something. And so let me just remark is that you can sort of understand this is, I mean, it's really very similar to the proof, the classification of simple algebras, basically. The classification of simple algebras goes pretty much the same way. So what do you do in the classification of simple algebras? You look at left, right ideals and the right ideals. So we consider a minimal sized left ideals and minimal sized right ideals. So in fact, so the simple ones are actually understandable. Then we have a little lemma, is that if I is a minimal, if I is a minimal two-sided ideal of A, then either I times I equals 0, or I is simple itself. Let's just try to do the proof here. Hope I got the statement correct. So proof. Suppose B is a two-sided ideal of I. Right, what does it say? I mean, we know there's no two-sided ideals of A that are smaller than I because I is minimal. So we'd like to say that there's no two-sided ideals in I, but it's not a priori clear that a two-sided ideal inside I would be a two-sided ideal of A because multiplying by A might be different. But then if we look at I times B times I, right? On the one hand, that's contained inside B, right? Because B is a two-sided ideal of I. But on the other hand, this thing is kind of obviously a two-sided ideal of A. Right? Because if you multiply here by A, right? I is a two-sided ideal. So if you multiply here or here, then you stay inside I. So this thing is preserved. Okay. So but since I is minimal, then the conclusion is either since I is minimal as a two-sided ideal of A, then either I bi equals I, or I bi equals 0. Okay. So if I bi equals I, then here we get B equals I, and we're sort of done for that part. Right? That's what we're trying to prove. We'd be trying to prove that if B is a non-zero two-sided ideal of I, we'd be trying to show that it's equal to I, right? So that's this case. Now suppose I be I equals 0, then that means that step here. So there's a case 1, which is both I times B equals 0 and B times I equals 0. Case 2, one of I times B or B times I is equal to I, equal to B. So suppose B is a minimal. We can take a minimal non-zero two-sided ideal of I, considered as a group itself. Okay. So one of these two is going to be equal to B. And then we get so suppose right. Suppose I times B equals B, then B times I is equal to I BI, which equals 0. Right? We're treating this. We're now doing this case. So in any case, we can always assume that. So conclusion in case 1 or case 2. We can always assume that I times B equals 0. Okay. Now let's let Z is a set of elements little z in I, such that I times little z equals 0. Okay. But the claim is that this is a two-sided ideal of A. Because if you multiply your z times A over here, then I times that is still equal to 0, right? Let's do that. Right, if you multiply z either on the left or on the right by A, then you still get 0. Okay, so z is a two-sided ideal of A. So the conclusion is that either z equals I, which is the case I times I equals 0, or z equals 0. But we have B contained in z now. Right, because I times B equals 0. So but B equals 0 is a contradiction because B was a non-zero minimal two-sided ideal. Okay, so that completes the proof. Right, there was two cases: either B equals I, that's this case, or B equals 0. Oh, sorry, or I times I equals 0. So the conclusion of this lemma is that we can make a canonical filtration. So by filtration, I mean a filtration in the F1 sense, which just means a sequence of subsets. So the corollary is that there exists a canonical filtration uh, 0 equals A0, containing A1, and AN equals A, such that, so what we would like to do is we would like to take the first step of the filtration to be some minimal two-sided ideal. But that's not canonical, okay? But how can we make a canonical filtration? It's the SOCL, right? It's the polystable subbundle. So this is the so-called filtration, in fact. And the condition is that each A I mod AI minus 1, the mod in that sense of just contracting that to 0, is polysimple, you might say. i.e. wedged together of simple objects. This case where the multiplication is 0, that's also simple. I mean, that's also polysimple, right? Because a semigroup that with a 0 and a 1, such that 1 squared equals 0, that's also simple. So I wouldn't exactly, so, right, the proof is just choose, let A1 contain an A be the union of all minimal two-sided ideals. Right, so A1 equals a union of I, K, okay? But now notice that I, K intersect I, L equals 0, right? Because they're distinct. We take the distinct one, so that's not equal. But since they're minimal two-sided ideals, the intersection is also a two-sided ideal. So, and it's a sub of either one of them. So since it's minimal, then that has to equal 0. Okay. And the multiplication, so the multiplication on this thing, sorry, A1. The multiplication on this thing is just obtained by saying the product of any two distinct things is 0. Because the product of an element of IK and IL is going to be in the intersection, so it's 0. And then continue by induction. So that's what I meant by saying that if you know something about vector bundles, then this all seems very natural, actually. So I wouldn't say this is exactly a classification, but this is sort of a start to a classification. I mean, it's a sort of some structural result. Now, let me comment here, so I should have said this before maybe, but let me comment that the classification of finite semigroups is well known to be a difficult theory. I probably should have said if you have a semigroup that doesn't have a 0, you can also just formally add the 0. And once again, that's not exactly an equivalence between the two setups, but roughly speaking. So the classification of finite semigroups this was done by someone named Distler. It was kind of a major paper, I guess, in computer science for size less than or equal to 10. And apparently size 10, oh, this is what David said, size 10 took like 900 years of computer time or something like that. Maybe that was a decade ago, so maybe we can do better, but.
Why was this a big paper in computer science?
Sorry?
Why was it a big paper in computer science?
Because it's a question of doing SAT problems, of constraint satisfaction problems. It was viewed as a application of the theory of solving constraint satisfaction problems. That's what David said. So I guess you might say one possible long-term hope here is that I think this is maybe dreaming or something. I think it might be possible to go beyond that by using this structural result and some kind of computer like AI type stuff. So question. I mean, I'm sure that if you apply the techniques that he used, then you should be able to do more now with new computers and so on. So that's like maybe one. So I don't know. I think you might be able to get up to 20 or something. But anyway, I'll illustrate in a minute why there's a combinatorial explosion and how you have to be careful. But maybe a little bit more, maybe slightly more relevant to what I'd like to say today is that, so these are really big numbers of stuff. So these are, okay, so I think that it seems to me a natural question we can ask is there some kind of probabilistic approach? So to understanding what might be called the classification landscape, that's maybe, I know that the word landscape is overused here, but. So for example, just a first question, can we get an estimation for the size? Can we estimate the order of magnitude of the number of semigroups? And so as we can see here, it's a logical further refinement of that, which is important for a reason which I'll explain in a minute. A logical further refinement of that, since there's other ways of making canonical, you can make a canonical lattice index filtration and stuff like that, I guess. Which I don't understand how to do, but apparently. But this is just like an easy thing you can do. Given that there's a canonical filtration for an object, that means that the subquotients of the isomorphism class of type of the subquotients of the filtration, those are invariants of the object. Okay, so we could fix those invariants. So we could say, so suppose we fix the invariance of the subquotients of the canonical filtration. Let's call it the so-called filtration. So this is one canonical filtration. You could also say, well, we could also make a co-so-called filtration. I think that exists. I didn't do the lemma for it, but you could like take the, I guess, the minimal two-sided ideal such that the quotient is polysimple. That's not necessarily going to be the same filtration. I guess, right, what I should say is that when I say there's canonical, it doesn't mean there's a unique filtration such that this property. It means that here's a canonical construction of a filtration, okay? There would be another canonical construction where you take the co-so-called filtration. And Pranav was saying that maybe his work with Kontsevich and Katsarkov and Haydn about R-index filtrations, you might also be able to have like a balanced filtration, possibly. Maybe. No.
Numerical data.
Sorry? Yeah.
Provide some numerical data that returns.
Yeah, but you could just like take constant, for example. But yeah. It's a little bit like, the Deligne canonical filtration for a nilpotent operator, right? Where you have the kernel filtration for a nilpotent operator. You have the co-kernel filtration. Then you have the Deligne canonical filtration, which sort of balances halfway between those two. So I guess there's probably lots of canonical filtrations. So that's why you need you can refine more data. But let's just suppose we talk about one fixed filtration. So we could say fix the invariance of the subquotients. So remember that the classification of the subquotients is pretty well defined. The only thing you'd have to worry about here is that, and the group is an invariant up to isomorphism, I guess. The only thing you'd have to worry about here is you have to worry about permuting the sets I and J and how that acts on the matrices there. But roughly speaking, we understand perfectly well the classification of simple objects, okay, and therefore of polysimple objects. So you might say, let's fix the invariance of the subquotients in the filtration and then ask how many solutions there are. And can we estimate that? Of course, even better than just estimating for some fixed value would of course, give some kind of asymptotic information. And the computer's not going to give us any kind of asymptotic formula, probably. But so now what I've been interested in, so I should say thanks to Soren, in fact. Soren, as director of our department, said, Carlos, you should apply for this 3IA thing. So Soren was the person to thank for that. So I've been working a lot on programming machine learning. So this, let's say this looks like a question that should be amenable to machine learning. That's what I like to talk about next. So let's just be specific. In other words, fix a filtration. Fix some data. Like this, like the fix some data like the classes of the subquotients of the filtration, and ask the computer to either search for, count, and predict how many answers there are. So before getting to that more specifically, let me just, so I guess I should have illustrated this, but let's maybe not let you guys do that as an exercise. So to understand this thing, which I'm about to erase here, no, sorry, I erased it already. To understand this Rees matrix semigroup thing, you should first just write down the case where G is the trivial group, right? You have two sets I and J, then you can make a semigroup where I think it's called the rectangular band or something like that, where I comma J times I prime comma J prime. We should just write this. In case G equals 1. I comma J times I prime comma J prime is just I comma J prime. Right? That's the easiest example. So once you see that you can make an associative multiplication line that way, then you can sort of imagine doing it with a group and so on. So the other thing I wanted to say was, which is an important comment, which is that there's some subfamilies which have an extremely large size. Okay? So the basic case is called 3 nilpotent. The 3 nilpotent case is suppose x times y times z is always equal to 0, right? Then it's automatically associative. And let's just do an example. So, a typical example. So our objects are always called 0 up to 1 up through n minus 1. And here, since we're doing categories with only one object, n is no longer the number of objects in the category, n is the number of elements of the semigroup. Okay. So suppose we say, I guess 0 is automatic. So let's just say 1 times x equals 0 for all x. X times 1 equals 0 for all x. So 1 multiplies to 0 with anything. And x times y is always element of 0, 1. Of course, if x and y, or if one of x or y is either 0 or 1, then we already know that the answer is 0. But now we're saying that any product of the rest of the stuff has to be in 0, 1. Okay? And then if we take x times y times z, or x times y times z, this is already in 0 or 1. And then multiplying by z, you get 0. And this is already in 0 or 1. Multiplying by x, you get 0. Okay, so when I say that, you know, x times y times z, it means x times y times z are equal 0 for for the both parenthetizations, maybe I should say. Okay, so this is automatically associative. And the number of solutions is, for these constraints, I mean, we just have to, for every x and y, we have to put a 0 or 1. So there's 2 to the n minus 2 squared. So for example, if n equals 10, this is going to be 2 to the 64th solutions, which is 2 to the 10th to the 6th, which is 10 to the 18th, right? Very rough count. So here, just automatically, you get more solutions than you could possibly write down. You're not going to write down 10 to the 18th solutions somewhere. Okay. On the other hand, so the guess here is that if you take filtrations like this, and you start putting actual simple things in the filtration, then you might say the guess at least is that that should cut down quite radically the number of solutions. There may just be a few solutions, for example. And so one of the goals of doing this on a computer in terms of theoretical information would be if we can put some examples into the computer and come up with at least an estimate of the number of solutions, then we should be able to get a better idea as to what precise kind of numerical thing we would expect in terms of this, what I just said, that in terms of what are the precise subquotients of the filtration, how many solutions do we expect to get, basically. So then you might be able to prove a theorem. I mean, if you see that there's only a few solutions in some cases, then you might be able to go and prove a theorem that says, you know, in those cases, even in general, there's only a few solutions. So that's, you might say, you might say, okay, well, but we're just going to calculate some stuff with a computer, so we're not really interested in that for any theoretical reasoning. But the point is that to do theoretical reasoning, you should first understand the answer to your question somehow or other. So let me just go out on a limb here and say that what did Ramanujan? He just knew the answer to the question, but he didn't know how to explain why. So the idea is to try to have a computer do the same thing. So the computer might just kind of know the answer to the question. Okay, so now let's how are we doing for time? Okay, so let's do a little bit of crash course on neural networks. So what's a neural network? So we're just going to do a multi-layer perceptron or something. And that's also known as a feed-forward neural network. So my claim is that this is actually a concept that's really easy for mathematicians to understand. And that since when you type a Gmail message, for example, it auto-completes your phrase. And it's using technology like this, I'm sure much better, obviously, than the simple version, but this type of technology. So I mean, this type of technology is surrounding us in the everyday world now. So I think it's important I'd like to just give in case you don't know what one of these is, I'll explain it to you in a minute. And you'll see it's extremely easy to understand. So there's nothing mysterious about what one of these things is. But I'd also like to make a comment, which is that historically, mathematics has always been generated in some sense by economic reality. Right? Remember, the first mathematics was people who were trying to count how many bushels of wheat came from their field, right? They weren't just like inventing numbers because they thought numbers were great. I mean, they wanted to count how many bushels of wheat they got, that type of thing. And I think this is an example. So you might look down upon, for example, the idea that people are using, whatever the big computer companies are using artificial intelligence to like send us ads that are adapted to our own consumption profiles or whatever, and that type of thing. But that's actually motivated by economic necessity, not necessity maybe, but by some economic motivation. But it's actually generating new mathematics, I think. So I think you'll see that there's new mathematical capabilities that have developed because of this, actually, and that we wouldn't have developed on our own, because you'll see in a minute when I tell you how this works. You'll understand that you wouldn't want to actually program that yourself. I mean, that would be like the biggest disaster of your entire life if you wanted to have actually programmed that yourself. But the fact that like publicity is paying for large groups of people to set up this programming stuff, then it makes it that now it's there. Okay. So what's a feed-forward neural network? So we're going to have an input, then we're going to have some layers. The other thing I understood is that these computer people, they multiply matrices the same way we do, but they view the operation in the opposite direction. So they view the operation, the input, as the vector coming in on the left, sorry. They view the input as the row vector coming in on the left, and multiply by the matrix, and that's the output. Okay. Whereas we view the input as being the column vector on the right, usually. And so, but anyway. So we take an input vector. Then we multiply by a matrix. So we get, then we get a new vector. That's a linear layer. Then this new vector, we transform it to another new vector, where we apply a nonlinear term by term. So this is linear. Okay. So you take a vector, x1 up through xk. Then we'll get a new output vector y1 up through yl. Then we'll have like y1 prime up through yl prime. So it's just that yi prime is just some nonlinear function of yi. There's no cross. The nonlinear term is just applied term by term on the vector. There's yi doesn't depend on yi prime doesn't depend on yj. Okay? The way that the terms of the vectors interchange between themselves, that's governed by a linear matrix. Okay. And the typical function here is one called relu. This is kind of a joke in French because when people say ça c'est très relu, that means it's like really not really totally on the up and up, you might say. I guess, yeah, relu. Relu is verlan for lourd, which means heavy. So anyway, this is like rectified linear or something or other. This is the function just y maps to max of 0 and y. This is like a typical function that you use, and if you might use it on a different function, but it's going to be some modification of this function, basically. That's a typical function. Then we just keep doing that, okay? Then we have a new linear layer. Then a new I mean, here again, we just multiply this new vector by a matrix, okay? Is that perfectly clear for everybody? This is supposed to be 100% perfectly clear for everybody, okay? We just take our input vector, multiply by a matrix, apply term by term a nonlinear function, there's nothing complicated, multiply by a matrix again, apply a nonlinear function, and so on. And then we finally get an output vector. So that's a good point. The nonlinear functions are staying the same, so usually. So these are fixed. And the matrices have coefficients. Okay? So yeah, so that's an important point, thank you. So this is the structure of the feed-forward direction of the neural network. So we have our neural network depends on the coefficients. And it gives you a function from input vector to output vector. Okay? So you might say on a theoretical level, if you use this function, for example, a theorem is that any piecewise linear function can be expressed this way. So I'm sure everybody's thought of, okay, if I have a function, let's try to approximate it by a piecewise linear function. But of course, the mathematician is going to say, okay, what are we going to do? We're going to make a triangulation of our space, and at each vertex of the triangle, choose the value of the function and make a linear interpolation on the simplices or something horrible like that. But you would never want to calculate that. This thing is like a really good sort of implementation of a general piecewise linear function. And any piecewise linear function can be expressed this way. We have a neural network which depends on the coefficients of the matrices. And it gives you a function that takes an input vector and gives you an output vector. Okay. Now what about training? So that's the machine. Now training the machine. No. So the coefficients of the matrices, this is what's going to be modified in training. So I mean, like the overall global situation is that we've got some function that we don't really know what it is, but we have some values for the function, and we would like to find the best approximation of a function like this that approximates the value. So you train the machine. To train the machine, you just you have a sample collection of input, output. And then you take, you apply the neural network to, let's call this X, and it's called like Y or something. You take the neural network on X, right? You have a collection of you have a large collection of samples which are input, comma, output. You'd like to create a function which approximates, which should have these values. So you apply your neural network to Xi, then you compare with Yi, then you take some kind of, so it's called like a loss function. But it basically means like the absolute value of the difference or something like that, or the square of the absolute value of the difference. Then there's a little complicated thing, which is actually, you don't do this just for a single input at a time, you do it for like a small collection called a batch of inputs at a time. Okay, then we would like to so we'd like to make that go down. All right, so this whole thing is a function of the coefficients. Let's call them like the alpha i's or something. Right. So for every pair input output, you get a function of the alpha i's, which is how the error term between the predicted value and the actual value. And we just gradient descend the alpha I, gradient descend to the values of alpha I to try to dot. To try and minimize this. Is that clear? So, I mean, it just means that a single step of gradient descent is we're going to follow the gradient. So this is we think of this as a function of the alpha i's. We're going to follow a short time the gradient vector of that function to try to modify the alpha i's to make this smaller. Then you do that on all the different outputs, like all in a row, basically. But you should randomize them. I mean, there's a whole theory of this, obviously. It's called loss. So you need to define a function which tells you how you're going to measure the error term. So that could just be the value, absolute value. But in fact, when you do this, you don't just do a single value of the input-output. You do like maybe 16 or something like that. So the loss is going to be maybe like the sum of the absolute values divided by some normalization or something like that, or the norms, or the sum of the squares, for example, or something else. And this is made possible by automatic differentiation. Again, a mathematician is going to say, okay, we're going to do that. So what are we going to do to calculate the gradient? Well, we'll take alpha I, and then we'll choose alpha I plus epsilon, right? And then calculate the value here and the value here, and then use that to calculate the gradient or something like that, right? No. But that's why this takes a lot of computer programming skill, somehow or other, is that this whole process is just a function that, I mean, this forward process is just a function that you put into the computer and it's going to compute. And there's a technique where the computer can go back over its own program and apply the chain rule. You just have to apply the chain rule. But you wouldn't want to calculate yourself the chain rule, right? The thing about automatic differentiation is you specify the function, and the computer calculates the chain rule and so on to calculate the gradient. So the computer calculates the gradient for you. You don't even see all this stuff. I mean, you just have to define this stuff basically, and you have to define this, what's the structure, namely the size of these matrices. That's about it. And so it calculates the gradient by automatic differentiation to get the gradient. And so this has been done by a number of different systems. I think it's like PyTorch. That's the one I'm using now. TensorFlow. Keras. I guess PyTorch is like Facebook or something like that, maybe. Dan, you said it was Facebook? Yeah. TensorFlow is Google. Yeah, I think it's open source, but I think it's and Keras is Keras Amazon or something? No, that's like more general, actually. Yeah, anyway. Dan is a big expert on this whole thing, knows how to do this much better than I do. Okay. Anyway, but you can see that, I mean, these are companies that are employing, tens of thousands of people and so on. Because when you're trying to figure out how to get from here to there, like you guys are using this all the time, right? Trying to figure out how to get to downtown Bangalore without spending all your time in traffic. I mean, it's doing this basically, if I'm not mistaken. Right? It wants to know, what the traffic conditions are going to be. So that's your input-output, right? How much traffic is there on a given road at a given time? It's predicting that way. I'm assuming they don't have they probably have passes of satellites to check, right, to generate the data, but they're not having satellites that are checking all the roads all the time, right? So they're predicting how much traffic is on a given road at a given time by doing exactly this type of thing. I mean, I'm sure it's infinitely more sophisticated than the basic thing I'm saying here, but this is the basic idea. For traffic flow? I don't know, but I'm just guessing. But I mean, the output is how much traffic there is, and the input is probably just the time or something. I mean, it could just be. I mean, it's the time of day plus the coordinates of which piece of road you're on. But I mean, if you wanted a neural network for just a given stretch of road, it would just be the time of day, maybe. I mean, or like maybe like the weather, you could put it. the weather, like holidays. I mean, any kind of factor that's going to affect the output. And so you can do gradient. So this stuff does gradient descent. And so one of the things, which is something we kind of came up with when David Alfaya was visiting in Nice. We're not obviously the first people to think of that, but we were thinking about this when David was visiting us in Nice, which is that this whole framework, I mean, this is the way you do it to do gradient descent for your neural network, but that will do gradient descent for anything you want, especially if it's made up of matrices. But I mean, but it doesn't need to be matrices in the sense that it'll calculate the gradient of any function for which it's cooked up to calculate the gradient. So like exponential, log, trigonometric functions, I'm assuming. I mean, any function which they've inputted into the system. You just need to know, how to calculate the derivative by a formula, I mean. So I'm not sure how far can I go, Dan? Maybe you have a good idea about this. 100,000 maybe?
Yeah. No, I mean millions.
Millions of variables, yeah, okay. 10 million? No. Let's say a million. Well, let's be conservative. 100,000 variables, okay. You can have a function of 100,000 variables, and this will do gradient descent on that function. Whereas when you're doing calculus, you're thinking it's really hard to do gradient descent on like a function of 3 variables or something like that. But I think this is an important thing for algebraic geometers. And then that's what I was saying about the Kempf-Ness functional. I mean, I think it should be essentially trivial, but it would take some work, obviously. But I think it should be pretty easy to plug I mean, if you try to write down like on P1, for example, especially, but even if you have a curve, you could project it to P1. Just try to write down, what's the precise Kempf-Ness functional for the O of minus n to the P of n into E. On P1, I mean, if you try to write down the Kempf-Ness functional, explicitly for this type of thing, right? I mean, E is just going to be a direct sum of line bundles on P1 and stuff like that. That's just going to be exactly writable in this type of form. Okay. And so I don't think it should, I mean, I'm not sure, as I said, one would have to do this, but it doesn't seem to me that it's going to be that much of a problem to just really do the gradient descent for this stuff. So maybe there's like a small caveat, but I'm sure they'll fix this soon, which is that, as far as I know, at least PyTorch doesn't really do differential equations in the sense that it has its own differentiation thing where it calculates the derivatives, but it doesn't like to recalculate the derivative of the derivative. I mean, there's no reason they couldn't do that. So you should, in principle, also be able to solve differential equations too. You should be able to include differentiation in this whole process. And I guess, I don't know about integration, probably, I'm not sure about that. So, you should be able to just like solve the Laplacian equation or something like that just explicitly. So it seems to me that that's probably like a new thing which will be happening in mathematics, in the next X years, which is that I think if people start saying, hey, this is a fun thing to use, then, yeah. Okay, anyway, that's my remark on that. Maybe can we get the screen? The screen? Okay. Okay. So let me just show you a little. It doesn't really work actually, unfortunately. So this is it's big ideas, right? But making it actually work is not so easy. But let me just show you. Yeah. Sorry about this, but I need to. I just did a PDF printout of my Jupyter notebook file. So maybe this is a little bit instructive at the start. So we're just putting some what I'm calling masks into the machine. So I didn't say that. I should have said that, but that's really fundamental to what's going on here. But running out of time. But let me just. So this is a mask, okay? So when you're looking at this problem, when you want to sort of fix some data to determine a semigroup, then the thing, pretty quickly, it's called multiplexing the data. You don't want to look at the multiplication table. The computer is not going to like reading the multiplication table. The reason is because the entries of the multiplication table are themselves places in the vectors, right? If you say I times j equals k, that means that the k thing is a location in the vector. So it's not the same type of thing as a number. I mean, it's not really a number, it's a location, right? And so instead, it's better to replace that by something with just numbers. So instead of a n by n array, which is the multiplication table, you use an n cubed array, n by n, which we're calling the mask. So the way to think of the mask, so this is the table here. Do you guys see the mouse? Do you guys see the mouse? Yeah. Right. This is the multiplication table right across here and down here. But this mask, like this one here, this is all the things where x times y could equal 1. I mean, x equals 0, 1, 2, 3, 4, 5, 6, 7, or maybe 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7. Yeah, this is like an 8 by 8 thing. 0, 1, 2, 3, 4, 5, 6, 7. So these are all the places where x times y could equal 1, possibly. And a 0 means it's not allowed to equal 1. These are all the places where it could equal 2. These are all the places where it could equal 3. So this is the mask for a nilpotent, what I'm calling an ordered nilpotent semigroup. So something where the multiplication only goes down, right? So for example, 6 or 7, the multiplication of 6 or 7 together could equal 5, could equal 4, and so on. But 6 times 6 is not, that's down here. 6 times 6 or 6 times 7, they're not allowed to equal 6 or 7. Okay? 7 times 7 is allowed to equal 6. And 7 times 7 is not allowed to be anything. So do you guys see that? So you're saying that you have, it's just, I mean, it's the case of this filtration I said. It's the case where in this filtration, all the quotients have size 1, and they're the 0 thing, right? So it's the case where you have the filtration, but that ideal is actually the 0. It's the case I times I equals 0 here, basically, right? So that's a mask. And then more technically, the problem which we're trying to solve here is, given a mask, how to count how many there are. So let me just go back to here. I know, sorry, this one. So let me just show you my neural network. Where's that? So here's the neural. This is what you need to write into your program. Of course, you have to do a lot of search on the internet to figure out where you're supposed to write that, but this is PyTorch. It has like predefined everything. So you just tell it LRL is this leaky ReLU, which is like a ReLU, except there's a little slope at the bottom. This tells you have a linear, these are the linear layers, matrices. Then this is the forward function. So given the input, you have to do something to put it into a good form, but given the input, then you apply this first layer, FC input ML, to go from the input layer to the main layer size. Main layer size is 40, I think. Then that's the first matrix. Then you apply LRL, that's the nonlinear function. So this means apply the matrix and then apply the nonlinear function, okay? Then we do that, then we go down from a 40 size vector to a 20 size vector, 20 to 20, and then 20 to output, basically. Typically, you sort of reduce the size, at least in the basic stuff I know how to do. And here I actually just output it. You can define something which outputs like the output of the first layer, because I was actually using that as input. I don't know if that was a good idea, but I was trying to use that as input into the second, the strategy learning thing. So the strategy learning thing, it's concatenating together a main layer output from the first machine, plus some other stuff, plus, I guess, the data of which choice you're making or something anyway. Then you define the criterion, which is the loss function. That's what I was talking about there. You write something that's called optimizer. That's the thing which is gonna, that's the big complicated thing which is gonna do the gradient descent and everything for you. Then let's see. Then typically, the code where you're doing some training basically works like this, that you give it the input data, which is like, it's like here. Input data AM, input data AQ. You apply this thing called SGNet, that's what I call the neural network. That's the neural network. Then you get the output. Then how do you train? You say the loss is equal to the criterion between the output. Well, sorry, that wasn't good. Let's do the B. The loss is the criterion between the output and your known piece of data, basically. Then backward, that's doing the gradient descent. An optimizer, backwards calculating the gradient, and then optimizer is doing the gradient descent step. Anyway, so let me just show what happens here. So here I'm really trying to run two things at the same time. The first is trying to calculate how many solutions there are. So we kind of explained that this is one thing we would like to know is how many solutions are there. So this is calculating how many solutions there are at each step. What's this? How many solutions are there at each step of the proof? Okay. Maybe I should put this back to full screen. So that's the prediction for how many steps there are after just a single segment. Sorry, that's the prior predictions for how many stuff there are. Let's not talk about the strategy one because that doesn't really work. But let me show you just the predictions of how many there are. That's the prediction after training. I'll explain what these graphs mean in a minute. Dan, you can look at my strategy training stuff as it blows by and see if you have an opinion on that. This is again after training, the predictions of how many there are. So what's happening here is we're doing a proof. We're doing a proof by dichotomy. So you're starting with this just the full nilpotent mask, and then you're saying, okay, let's suppose that like 3 times 5 is between 0 and 2, or let's suppose that 3 times 5 is I guess either 3 times 5 equals 0 or 1, or it's equal to 2 basically. It has to be less than 3. Right? So that's a typical cut. It's like you cut into 3 times 5 equals 0 or 1, or 3 times 5 equals 2. That divides the proof into the classification proof into two branches. Then you just keep dividing like that. And at each branch you have a mask that tells you where you are in the proof. And then you'd like to know how many solutions are there for that mask. That's all these different data points here. So it's like calculating. And so what's the neural network trying to do? It's trying to figure out just from the mask how many solutions it expects there to be. So these are, of course, special masks because they're the ones that you obtain by doing these cuts to the general nilpotent thing. So it's not all that general, but I chose to do the nilpotent thing because you can kind of imagine from here, it looks to me, I mean, just intuitively, it looks like if you put simple semigroups that are not zero inside the filtration, I think that's going to make a lot less solutions. So like the typical, I mean, you can see from my example with 2 to the 64th, the place that generates lots of solutions is the nilpotent case. And this is 6 by 6 nilpotent case. So after 2 training segments, so segment 2, that means that we're doing 6 proofs at a time. So we've done 12 proofs so far. Maybe I should. Let's go down to the bottom of the file here. So after doing 180 proofs, that's the prior predictions after we've done, probably 100 proofs or something like that. So you can see, so I drew on, so this graph, the axes are logarithmic, so it's log to the base 10. On the bottom, it's the real value, because when you do the proof, then you get to the end and you calculate the actual value. Okay? So on the bottom is the actual value calculated by the proof. And on the y-axis is the value predicted by the neural network. And the green line is the diagonal. The red line is plus or minus log to the base 10 of 1.5. And the yellow line is plus or minus log to the base 10 of 2. So for example, if you're on the yellow line, then it means that, that you're off by a factor of 2. If you're on the red line, it means you're off by a factor of 1.5. The actual number is off by a factor of 1.5. And if you're on the green line, it's like you're pretty close to the actual number, actually. I mean, it's not going to tell the difference between like, so I should say the total number of solutions for this problem of 6x6 nilpotent is 89,251. I know that number very well now. There's like 89,000 total solutions. That's like, we don't see that point. I mean, this is just a sampling of the data, so we're not seeing the sample of the root of the tree here in this graph. That would be like almost at the 5, right? It's almost 10 to the 5th. 100,000 is 10 to the 5th, right? But so you can see that it's not going to tell the difference between, you know, like 30,000 and 31,000 maybe. But it's going to tell the difference between like 30,000 and 40,000. And it's going to tell the difference between like 10 and 12 or something like that. So, I mean, it seems like those are actually, it's actually pretty good. Those are pretty good results, but that's for the counting problem. Unfortunately, for the strategy problem, the results are much less good, right? The strategy problem, so the idea is to, at each step of the proof, you have to choose one of the possible dichotomies to use. There's a bunch of different choices. You like to like choose the best one to finish the proof in as small time as possible. So you like to like have it, one idea is to have it predict, Dan was telling me this isn't quite the right thing to do, but anyway. One idea is to have it predict how many solutions there are going to be for each choice, then choose the lowest one, basically. But it's having trouble predicting that. So anyway, so I don't have anything great to say for that. But I'm hoping that after some significant fine-tuning and stuff, coming up with the right system, that should work. But I hope you can at least get the idea of what the neural network is doing. This is prior predictions. It means you've loaded the proof, you've done the predictions without actually training the network on that set of data. It's kind of a similar set of data each time, but yeah, so anyway, awesome.
Oh yeah, okay. I just had a background question. Is this problem known to be NP complete in some sense?
Oh, I'm sure it is. I mean, I don't know, but yeah. I think what David was saying was maybe it's like there's like subclasses apparently in NP complete or something. Maybe it's, I'm not sure, but
okay.
The questions? So you mentioned in the abstract that this is related to the moduli problem in algebraic geometry.
Oh yeah, sorry, I should have said that. If you've got a semigroup, then you get an associative algebra. So you can look at the derived category of the associative algebra, or you could look at its moduli space or something like that. So I mean, every one of these points, this is like 89,251 possible derived categories, right? And so another thing you might want to try to do, I mean, the other types of, and the AI people do lots of different types of things, among them like clustering. So you might try to apply some kind of clustering thing and like understand the properties. So I mean, one type of thing, of course, going to be probably kind of complicated to generate the data, but you could say, okay, like what's the dimension of the moduli space, for example? You could try to predict for all these things, what's the dimension of the moduli space? So you'd think that the neural network might possibly be able to give you a prediction of the dimension of the moduli space, or like what's the Hochschild homology of the category, or like another thing was a good thing was this Orlov gap spectrum thing. So you might try to calculate anything you want to calculate. Yeah.
There is a very similar, kind of similar question. A guy who is actually in Madrid, currently in Madrid, whose name is Challenger Misra, is doing applying machine learning methods to, I think it was to do this kind of thing, like regression on, I think it was on the Hodge numbers of complete intersection Calabi-Gauss.
Yeah, I should have also mentioned, I mean, it's too much to mention. I have like a file with all the different papers on archive that are relevant to this kind of question. I mean, it's huge. There's been, in the past 2 years or so, there's been a huge number of papers about that. One of the first ones was called like machine learning, the string landscape or something like that. That sounds like it might possibly be related to the question of Claude-Biaus. So yeah, there's lots of people that are doing this type of thing. Yeah.
More questions, comments?
Well, if you think about it a little bit, there's no way you could possibly understand the proof of this type of thing. I mean, if you wanted to count yourself, take one of those points in the middle, take that mask. It's not going to be all that complicated actually, but it's just going to be, right? So it's an array with 216 things in it. Most of them are 0 because of the nilpotent property, and like just a few of them are. Like you have there's a couple of x's and y's where you might have 2 or 3 choices possible or something like that. Then you have to try to figure out how are you going to prove anything about that by hand? I mean, when you do a proof, I mean, one of these proofs is the shortest proofs are like 500 steps long or something like that. But each step involves calculations about the associativity property, which in principle could involve like n to the 5th calculations or something like. I mean, in fact, they involve less, but. Every time, I mean, you're saying x times y times z equals x times y times z. You're looking at all the possibilities and like calculating what that could possibly be. And so, I mean, one of these proofs has like 10,000 or 20,000 logical steps in it. So I mean, there's no hope of doing that by hand, I think, as far as I know.
Other questions? If not, let's thank Carlos again for a wonderful, fantastic lectures.
Thank you very much for listening.